Okay, welcome. This is the third section of our chapter 13, which is probability. And today we're going over compound events. Not all probability is based on only one thing happening. This is if more than one would happen. All right, so find each probability when a number cube is rolled. The probability of rolling a number divisible by 2. Okay, so what do we have? How many even numbers are there? So we have 3 even numbers, right? 2, 4, 6. Out of a total of 6, so I have a 1/2 probability. Probably rolling a number divisible by 3. What's divisible by 3 is 3 and 6, so we have 2 over 6, or 1/3 probability. Probability of rolling a number divisible by 2 or 3. Now, this is a critical point here, this or. Or means you're adding things, and means you multiply. So, this is going to be the probability of getting a divisible by 2. Plus the probability of a number that's divisible by 3. So that means it's 1/2 plus 1/3. Okay, so that's 3/6 and 2/6 is 5/6. We add them. Right? Now, we can do this if we look in this small group at the actual possible outcomes. So divisible by 2 is 2, 4, and 6. Divisible by 3 is 3 or 6. See, I'm wrong there. It's not that. But you have to subtract the overlap. I forgot because I have an overlap. Which is 6, right? 6 is in both of these two possibilities. Oops, I just took out my 3. Okay, so this is the probability that it's divisible by 2 plus the probability that it's divisible by 3 minus the probability that it's divisible by both. All right, the reason for that is there's this overlap. The easiest way to see this is in Venn diagrams. Okay, so I'm going to erase some of this so I can now do this with a Venn diagram. Now you can do it on, the edge of your paper or whatever. I don't have that luxury on this one. Okay, so if we look at it this way, I have divisible by 2, which is 2, 4, and 6. And then I have divisible by 3, which is 6 and 3. Well, notice I've got this overlap. So the 6 has been counted twice. So if I just added these two probabilities together, I get an extra one that's too big, right? So the equation for this is the probability of 2 plus the probability of divided by 3 minus the probability of the overlap, which is 2 and 3. All right, so what we get is 1/2 plus 1/3 minus 2 and 3, which is just 1/6, which is 6, right? So this ends up 5/6 minus 1/6, or 4/6. We have 4 possible outcomes divided by 4 correct outcomes divided by 6 possible outcomes. All right. Now, a simple event is an event that has a single outcome. A compound event is made up of 2 or more simple events. The probability of rolling a die and getting a number that's divided by 2. The probability of rolling a die, that's a simple event. Divided by 3, that's a simple event. Compound event is the 2 put together. 2 events are independent when the occurrence of one event has no influence on the probability of a second event. Okay, so rolling a die. What's the probability of rolling a die twice, and on the first roll getting a 5 and on the second roll getting a 3? What's that probability? Well, okay, those are independent because the roll of the first has no influence on the roll of the second. It's not going to change your probabilities at all, right? Dependent events are where what happens in the first one changes. So remember we had the hat with 4 marbles in it, 1 black and 3 blue, I think it was. If I take out a marble, let's say I draw a marble, what's the probability that I draw 2 marbles in a row and both of them are blue? Well, that first marble has a 3 in 4 chance. But now that 1 marble is out of the hat doesn't have 4 marbles anymore. It's 3 marbles now. 2 are blue because this one I drew out was blue. So with 2 blue, I now have a probability of 1 in 3 because I still have 2 blue and a black. So now that's changed. You see how the probability has changed? Those are dependent events because the fact that the first happened changes the probability of the second. Okay, so that's dependent. All right. An experiment consists of flipping a coin and rolling a number cube. Stop. Dependent or independent? Dependent. I'm sorry. Independent. Independent, definitely. Because flipping a coin and rolling a die, one does have nothing to do with the other. It's not going to change anything. Okay, so independent. Let event, A be the results of heads, a result of heads on the coin. And event B is getting a 2 on the number cube. Are these two events independent or dependent? We already decided they were independent. Independent. Okay. State the sample space and where the elements in the sample space are equally likely to occur. Okay, so our elements are going to be a heads and a 1, a head and a 2, a head and a 3, a head and a 4, a head and a 5, and a head and a 6. Okay, 6 of those. But then I also have the probability of getting the tails first. So tail and a 1, tail and a 2, all the way down to a tail and a 6. So that gives me a total of 12 possible outcomes. All right, now find the probability of A, the probability of B, and the probability of the compound event A and B. Okay, so the probability of A, rolling a die and getting a heads, is 1/2. The probability of B is rolling a 2, so that's going to be 1/6. Right? Okay, so now probability of A and B is 1/2 times 1/6. Remember I said and is a multiplication, so that is a 1/12. Well, if I look at all my possible outcomes up here, right, where is I'm looking for the probability of getting a heads and a 2. Well, I only have 1 right there. So 1 of the 12 is a heads and 2. There we go. Now you can write them all out in a fairly small situation like this. When you have a larger possibility pool, you can't really write all the answers, possibilities out and do it that way. So that's why you need to know how to compute the theoretical probability. Okay, so now, and 2 events are independent. The probability of the both happening, A and B, is a times. Okay, that's a times. All right. So, a bag contains 6 white balls, 3 red balls, and 1 purple ball. Okay, so we have 6 white. They're going to be blue today. 1, 2, 3, 4, 5, 6, and 3 red, and 1 purple. Okay, yes, I could do white, but you wouldn't be able to see it. All right, so these are my bag. It contains these different marbles. What is the probability of drawing a white ball, replacing the ball, and drawing a red? Okay. So these actually end up independent because I'm putting the ball back in. It's not dependent. If it was dependent, it would change things. This is independent. So it's, since I'm putting the ball back. If I wasn't putting it back, it would be dependent. All right, so probability of a white ball, in this case a blue, is I have 6 of them and I have 10 balls altogether. So that gives me 3/5. The probability of a red ball, I have 3 reds out of the 10. That doesn't simplify at all. All right, so now I have to multiply these two together. 3/5 times 3/10 is going to give me 9/50. Okay, that's a fun one right there. 9/50. That would be my probability of the independent event. Conditional probability is the probability of a dependent event, because the probability of the dependent event, the second event, is based on the probability or the first one happening. Okay, so it's the probability of getting a, let's see, okay, when I'm drawing the marbles, what's the probability of drawing a blue and then a red, white and then a red? Well, what's the probability of a red given that a white occurred? So what's the probability of drawing a red given that I've already drawn a white? That's what this is talking about. Okay, so for conditional probability, you're always going to have the word given. All right. Now, remember we did the trees before. So this is a tree with some probabilities in it. So, again, we've got the 6 white balls, 3 red balls, and 1 purple. So I can draw a white. Oops. I wanted that to be highlighting. There we go. I can draw white. I can draw red. Or I can draw purple. Now, if I draw a white, I can draw another white, a red, or a purple. Notice this possibilities for all of these, except one. You have to be careful. Notice since, this purple is not right. I only have 1 purple. I can't draw a purple and then a purple. It doesn't work. There's only 1 purple in there. So that's why this bottom one, after I draw purple, only has 2 possible branches, not 3. Okay, so my number of possibilities are 1, 2, 3, 4, 5, 6, 7, 8. Why does it say 9? Oh, because there's 9 balls in the container, right? I draw out 1. I have a 6/10 to get a white, 3/10 to get a red, 1/10 to get a purple. But that ball's going to sit on the table. It's not sitting on the table. It's not in the bag anymore. So now I only have 9 marbles in the bag. And if it's a white, if I drew a white, so I'm on this one right here, right? If I drew a white, then my next one, my white, isn't 6 anymore. I only have 5 whites in there. So it's going to be 5/9. My red is 3/9 and my purple is 1/9. Now if I drew a red, I don't have 3 reds anymore and I have 2. So reds are 2/9, with the whites being 6/9 and the purples 1/9. And I already showed you that I lose the purple if I draw purple first. So then I only have 6/9 and 3/9. Okay. So, a bag contains what is probability of drawing a white ball, replacing the ball, and drawing a red? That's going to be the probability of drawing a white times the probability of drawing a red. Okay, so on the second turn, white first, red second. So white first, red second is, there's the path I'm looking for. White first, red second. So I'm going to use those probabilities. It's going to be 6/10 times 3/9. Well, this becomes 3/5. 3 times 3 is 9, so I end up with 1/5 probability. Okay, so you got to know your fractions. All right, the probability of dependent events. If A and B are dependent, then the probability of A and B happening is the probability of A times the probability of B given that A has occurred, right? The probability of B, if A hasn't occurred, is different. So you have to figure out that probability if B has, or given that A has occurred. All right, formula for a second. Do some highlighting again. Okay. A, notice A is here, here, and there. And B is here. That order matters a lot. Nope, let's look at this. Now, sorry, I'm going to go back to the... All right, so a bag contains 6 white balls, 3 red and 1 purple. Same bag. Find the probability of drawing a red and then a white ball if the first draw is not replaced. So we're not putting it back in. So this is that whole dependent thing. So we're going to use this given formula here. So the probability of red on a first draw is going to be, is going to be 3, because we have 3 red balls out of 10. This is the probability of R sub 1, red on the first draw. The probability of white on the second draw, given that red has occurred. I have 6 whites still in the bag, because I've only drawn out a red, but I don't have 10 anymore, I now have 9. This simplifies to 2/3. So now I multiply these to get my probability of red on the first and white on the second. So I have 3/10 times 2/3. And the 2 turns this 10 into a 5. I have a 1/5 probability. Yay! All right. All right, contingency tables. Brown eyes, not brown eyes, male or female. A contingency table is a concise way to present information and can be used to solve your probability problems because you have all your totals and stuff. All right, so let's look at this. The probability, if these are the number of children born in a particular hospital on a particular day, and you randomly select one of those children, what is the probability that it has brown eyes and is a boy? Well, brown eyes and a boy, 6 of them, brown-eyed boys, over 18 total children. Simplify. Done. Okay? So these contingency tables there we go. Female is 5 out of 18, and total of brown eyes, male and female, is 11 out of 18. Are very convenient. All right, inclusive and exclusive. 2 events are inclusive if they can both happen at the same time. So, probability of rolling a die and getting a number greater than 2, and the probability of getting a 4. 4 is greater than 2. They can happen at the same time. By drawing a 4, you get both a 4 and a number greater than 2. Mutually exclusive means they can't. What's the probability of rolling a die and getting an even number and the probability of getting an odd number? You can't get an odd that is even, right? So exclusive is important to understand, right? That's where, remember, we subtracted the overlap in the Venn diagram. Mutually exclusive Venn diagrams, apologies, would look like this. No overlap. Odd, even. Okay? Inclusive means they have to have some kind of overlap. Sometimes one of them can be completely contained within the other, but there's still an overlap, obviously. Okay. All right, probability of A or B. If A and B are inclusive, in other words, there's an overlap, you're going to have to subtract out that overlap because you can't have it count twice. If they are mutually exclusive, no overlap, you don't have to worry about it. You don't have to subtract anything. It's just probability of A plus probability of B. So this is important to understand. All right. Using the contingency table, find the probability that a student chosen randomly from the class is female or has brown eyes. Ah, that was the contingency table we saw. Okay, these are actually people in a particular class. Randomly has female or has brown eyes. So the probability of female, let me go. Okay, they are inclusive. There is an overlap. You can be female and brown eyes. Oops, I see why I'm going over. Using a Venn diagram, we can see I have a total of 8 females and a total of 11 brown eyes. So you can see that the easy way to add this up is, there we go. We're just going to have to add these numbers together. We've got 6, 11, 14 over the 18 possible. Now, if you didn't put it into a Venn diagram and know all those numbers, you might add that 5 in twice, and that would be a problem. All right, and our last question. When a pair of number cubes is rolled, what is the probability of getting a sum less than 4 or greater than 9? Or means it can... Never mind. Okay, so these are independent events because you're rolling 2 number cubes, right? So they're independent. Okay, so when a pair of numbers, so it's going to be the probability of getting less than 4. How many numbers are there less than 4? 1, 2, and 3. So 3... Oh, wait, nope, sorry, sum. All right, this is a little trickier. I'm going to draw you a little chart, and it's going to help. Okay, so when we're talking about rolling dice, on the first die, I can roll a 1, and then on the second die, a 1, or a 1 and a 2, or a 1 and a 3, or a 1 and a 4, 1 and a 5, 1 and a 6. I could roll a 2 on the first one and a 1 on the second. 2 on the second. 3 on the second. So you get the idea of what I'm doing here. I'm writing out like a sample space. 5 to 6. I can get 3. And then all the possibilities. Okay. Now, the probability of getting less than a 4... Oops, sorry, that should be a 4, not a 3. 4, 1. We have 5, 1, and 6, 1. 2. All right, so now the probability of rolling a number and getting a number less than 4, well, let's see. 1, 1 is less than 4, 1, 2. 1 plus 3 is 4, so that wouldn't count. So those are all the numbers less than 4. There's really only 3 out of all the possible, which is 36. 6 rows, 6 columns. Okay, so now we also want to look at numbers greater than 9. So I have 6, 3, 6, 4, 6, 5, 6, 6. 5, 3, 5, 4, 5, 5, 5, 6, 4, 3, 4, 4, 4, 5, 4, 6. All right, so now let's look at the probabilities of those numbers. All right, so greater than 9. Well, that's 12 and 11, 10. Okay, but the others are all 9, right? 6, 3, 5, 4, 4, 5, and 3, 6 are all adding to 9, so they wouldn't be counted. So notice, how many do I have? I have, of the less than 4, I have 3. Whoops. I'm still in highlight. There we go. I have 3 of the 36. The greater than 9, I have 1, 2, 3, 4, 5, 6. Greater than 36. So I add these two together, I get 9 over 36, which simplifies to 1/4. All right. And there we go. And that's your homework. Have fun.